Hi there, it's Saturday Extra and it's Physical Sciences. My name is Tinyiko Kosa and I'm welcoming you as usual. We're going to have an interesting lesson today. We're going to talk about rates of reaction. So stay with me until the end of this lesson. Now, like I've already said, rates of reaction, and we will try and revise some terminologies and of course the collision theory. The terminologies, of course, will be based on reactions and chemical change. That's what we'll be talking about. We'll try and define what we mean by rate of reaction, and we will look at what factors affect rates of reaction. And we will also have a look at whether we can represent chemical reactivity or a process of chemical reaction into graphs. Okay, now let's move on. Let's start here with some basic revision on chemical change. We've done a lot on this, so I'm not going to spend that much time talking about this. Remember that when you have got chemical change, you would have substances reacting together. And those substances reacting together, we call them reactants, or sometimes we refer to them as reagents. Okay? So these are the reactants. These are the substances that are bumping on each other, interacting, so that they can give us some desired products. Okay? And I have already mentioned product. Now, what are products? This is what the yield is. Okay? What is produced? Substances produced in a chemical reaction. What is produced? That gives us the products. For example, we can have a situation. Let me take a hypothetical reaction here. Say a chemical A reacts with chemical B. These are reactants or reagents. They are going to give us a product. So remember, we don't use an equal sign for the yield or for showing what is formed in a chemical reaction. We use that arrow. And the product could be C, for example. Okay? So A and B are our reactants, C is our product. To come to real situations, say you have magnesium. Let me think of magnesium here, reacting with oxygen. Oxygen exists as a diatomic molecule. We know that what is going to be formed is magnesium oxide. And of course, that will be the chemical formula of magnesium oxide. You know by now why the chemical formula is like that, because in our very first lesson in the revision of grade 11 work, we did that. Okay, so in the same way, magnesium and oxygen are our reactants, and magnesium oxide is our product. Okay, now we shouldn't think that the product will always be something that is just one substance. We can have situations where what is formed is not just one substance. Okay, you may look at situations like maybe say you've got say magnesium again, and you react this with, say, sulfuric acid, okay? And what is going to be formed there? What is going to be formed is magnesium sulfate, okay, plus what else is going to be formed there? Magnesium sulfate, obviously hydrogen gas will be the product there. But then you see, you've got reactants here. Two of them, magnesium and sulfuric acid, are your reactants. Your products here, magnesium sulfate and hydrogen gas. So you still can have more than one entity, more than one substance being your product. That is possible. So we shouldn't think, oh, with the product I always have one substance. No, it can be two, it can be even more than two, depending on the chemical reaction that we're looking at. So that's a quick revision on chemical change. But then we also need to look at the collision theory, okay, under chemical change. What does the collision theory say to us? Remember what we did earlier on? Reacting substances or atoms, right, molecules or ions, okay, all these particles, when they react to each other, for them to react, they must have sufficient energy, and they must be oriented correctly, okay? They must be in the right orientation, right? So it's a question of energy, enough energy, and the right orientation, okay? The second thing about the collision theory that we need to remember is that during interaction or during bond formation, electrons are rearranged so that we can have new bonds forming, okay? So electrons we know that electrons are found in orbitals around atoms, okay, molecules. In that arrangement, for us to have new bonds forming, old bonds must be broken and new bonds must be formed. When the old bonds are broken, there is rearrangement of electrons. They could be moving from one orbital to another and all those kind of things. And at the end of it all, when the new bonds are formed, those electrons find themselves in a completely new position altogether. So there is rearrangement of electrons for new bonds to be formed. Okay. Now, let's come to the main part of our lesson. We're talking rates of reaction, and we want to look at how can we measure the rate of a chemical reaction. But before going up there, or before talking much about measuring the rate, let's unpack what we mean by this word rate here, rate. Now, the word rate basically means that something is changing per unit time. So something is being measured, the change of something is being measured per unit time. Now, if we are measuring the rate of reaction, it means we are looking at how fast a chemical reaction takes place. So we're looking at how fast a reaction occurs. How fast a reaction occurs. Right? So if we are to look at how fast a chemical reaction occurs, we need to find out the quantity, the changing quantity that we can look at per time as to how it is changing per unit time. In this case, usually when we measure the rate of reaction, we look at how moles are changing per unit time. So we will have number of moles there, and we use small n for number of moles. But then you would know that for us to get moles, n, all right, we can start from the mass as well of a substance. And from the mass, we can find out the number of moles available in that mass of a substance. So we can also say that the rate of reaction can be measured by looking at the change in mass over the change in time. And of course, like I said, this change in mass, you can calculate how many moles are in this mass such that you can say change in the number of moles divided by the change in time. And you're still talking about the same thing. And it is when you are writing this formula in that form that your unit of measurement for rate, unit of measurement for your rate of reaction becomes mole per second, Why? Because N, the number of moles, is measured in unit called mole. Okay? And then time is measured in seconds. Hence, we say that this is going to be, it's going to give us a unit of moles per second. It is because we come from there. We're dividing number of moles by the time in seconds. So the unit is mole per second. So the unit of measurement, if we have not converted into number of moles like we did to have that, say we stuck with our mass there, we know that mass in chemistry, we measure that in grams, so it would be a situation where the rate this time is given by mass, or M, divided by change in time. Now mass, okay, it's measured in grams. Sorry about that. So G divided by time is measured in seconds. So the unit we're looking for here will be grams per second. Okay? Grams per second. Now this change here, I need to explain thoroughly here. If we go back to the previous slide where we spoke about reactants and products, you would see that if I have magnesium, okay, if I look at this one, magnesium reacting with oxygen to give me magnesium oxide. To find the rate here, I can look at how much of magnesium is being used per unit time, okay, or in a particular period of time to find out the rate, okay? So I can look at the change in mass of magnesium, okay? And then if I measure the time it takes the magnesium to change from a particular mass to another, or from certain mass to nothing, if I have that time, then I will say that that change in mass divided by the time that I've measured will give me the rate, which will be in grams per second. Right? So I can look at that. At the same time, I can decide to say, okay, let me not look at how this one is changing its mass, but let me look at how much mass of magnesium is formed over a period of time. Okay? So for this one, I'll start from 0. And I will, after some period of time, I might be having some mass of magnesium that has been formed, and I'm going to use that mass over the time that I've measured, and I'll find the reaction rate in grams per second. Okay, so I can decide to use any of these quantities or any of these substances, depending on which one will actually be convenient for me at that particular moment, because the main aim will be to find the rate at which the reaction is taking place. Right. Now, before we move on again, perhaps let's look at this issue here of rate measured in mass and rate measured in moles per second. For me to use moles per second, it means I must convert, or I must find out how many moles are in a given mass. So if I'm given the mass of an object and I want to find the rate in number of moles per second, so it's moles divided by time, which is now mole per second, it means I must convert this mass into number of moles, N. What do? Remember, this is also part of the revision. Number of moles is always given by the mass of the substance that we're looking at, divided by the molar mass, capital letter M for molar mass. Remember this? Small m given mass. capital letter M, what we call the molar mass of the substance. Okay, so we will see how to look at that, but it's just quick revision. I think you know how to do the molar mass. If you're given, for example, magnesium oxide, you must know you are going to add the mass of magnesium into the mass of oxygen. Together they give you the molar mass of magnesium oxide, and that is the capital letter M for magnesium oxide that you're going to use there. Okay, so that is also important for you to note. Now let's have a look at an example. Let's look at example 1. The following reaction takes place where you have lithium reacting with oxygen and you're producing lithium oxide. After 2 minutes, 4 grams of lithium has been used up or consumed. Okay, calculate the rate of reaction in moles per second. You see, we are told in moles per second. Now, it means that we given mass, so we need to convert this mass into molar mass, right? Now, how do we do that? So we have 4 grams of lithium. Number of moles is given by mass divided by molar mass. What is the given mass? The given mass is 4 grams divided by the molar mass of lithium. You look up in your periodic table and you will find that lithium has a molar mass of 6.94. So you have 6.94 for M there, grams per mole. So what are you going to have here? You'll find that the number of moles you're having is 0.58, okay, mole. Okay, we can confirm that. You have your calculator if you're struggling to do that, okay, and you would say this is 4 divided by 6.94. And what do you get? You get that. You press the SD sign and we have your 0.58 moles. Now, what will be the rate? Okay, the rate is given by change in the number of moles. So it will be the number of moles here. Let me put that change in number of moles over the change in time. And what will be the change in the number of moles? The change in number of moles is that over the 4 seconds, 0.58 moles were consumed. So 0.58 moles divided by the time it took for 0.58 moles to be consumed is given as 2 minutes. Now again, are we working in minutes or in seconds? We're not working in minutes. We work in seconds. To convert into minutes, that 2 should be multiplied by 60 to convert into seconds from minutes actually. So what do we have there? You have got 0.58 divided by 120. You can again use your calculator here. Let's see. It's going to be 0.58 divided by 2 times 60. We know it's going to be 120 seconds. And then the answer is 0.048 moles per second. But then we can convert that. In fact, we can round off these numbers here, in which we're going to have this as 0.005. That's the first significant number there. So it will be 0.005. 5 because 8 is bigger than 4, and then it makes 4 the 5 there. So 0.005 mole per second. So 0.05 moles are consumed in a second in this chemical reaction. So that will be the rate at which lithium is reacting with oxygen to give you the product there. Remember, by just taking lithium and finding out that rate, you have actually found the rate for the whole reaction. It's not just for lithium, or if you took oxygen, you will say just for oxygen. No, it is the rate at which the reaction is taking place. So that gives us the rate at which lithium and oxygen are reacting to give us lithium oxide. Let's move on. And now let's look at factors affecting the rate of reaction. In other words, we're looking at things that will either make the reaction take place faster or slower. These things here include the following. One, we're looking at the type of reactants. What kind of reactants are we having? Are we having these reactants reacting in a solution form, for example? Are we looking at solutions? Are we looking at gases? Are we looking at solids? Okay, what are we looking at? And you remember that when you write your chemical equation, we want you to show the specific state in which your chemicals are. So for gases, you have G. For solids, you have S. Can you still remember what we have for solutions? Okay, when you have something in solutions reacting, okay, we put AQ for it, aqueous. Okay. So type of reactants, what are we having there as the reactants there, right? Temperature of reaction mixture, okay, at what temperature are they? Is it something cold, warm, hot, okay, right? All these conditions will tell us whether the reaction will be faster or slower. Okay, now the third one, concentration. Okay, what is this concentration? Okay, with concentration, we're looking at how many moles of a substance are found in a unit volume. Okay, moles of substance in a unit volume. In a unit volume. This is what we're looking at. Okay. Now, let me just go over all of them and then we'll go back to each one of them again and explain something. Now, state of division of solids. What are we looking at here? We're looking at things like the surface area. Okay. Surface area. And this also includes the size of whatever we're looking at, pieces of these solid substances that are reacting, okay? And the last one we're looking at, do we have some chemical that we can put in here, add on here, that will make the reaction take place faster, okay? In other words, with a catalyst, what we are saying is that this substance here, if we have it, a catalyst, okay, it is a substance that we can use to speed up the rate of reaction without the substance taking part in the reaction. So a catalyst is a substance that we use, okay, to speed up the rate of a reaction. The rate of reaction without taking part in the reaction. So it doesn't change. Remember, in a chemical reaction, there is chemical change. So for it to be just a catalyst, it starts as it is and ends as it is, but it makes the reaction to take place faster. So it does that without taking part in the reaction itself. That is what a catalyst do. All right? Now, let's go back again. Now, I want to start to try and unpack this, especially temperature concentration, and the state of division. Okay? Now, with the type of reacting substances, you would know that if you have got things in liquid form, okay, that's another one that I left out, in liquid state, and reacting with maybe gases, okay, these gases can dissolve in the liquid maybe quicker than when you are having a solid reacting with a gas, okay, that maybe might take place or might occur in a very, very slow pace. Okay, so this is what it is saying here with the type of reactants. But when you come to the second one, the temperature, you see when you heat things up, you make them to react quicker. Like when you make your tea from boiled water. Definitely you know that the tea inside the tea bag is going to actually dissolve into your water much quicker when you have got hot water. So when you heat things up, you make them to react faster. Okay? So when you heat up, okay, which is about increasing temperature. Okay? So increasing temperature. When you do that, you make things to take place faster. So here, all these makes the reaction to be faster. You're making the pace of the reaction to be faster when you heat things up. In the same way, when you cool things off, when you put things inside refrigerators, in cold storage, you are saying, I don't want reactions to take place faster here. I want the reaction to take place slower. It's like, for example, when you're putting your food in the fridge, you're saying that I know bacteria are all over, but I don't want them to get my food to rot quickly. So I will put this in a cold storage. You are doing that because you are slowing down the rate of reaction between bacteria and your food. Okay? So that's what we need to understand about temperature. With concentration, all right? Concentration, like I said, it's moles of substance in a unit volume. The more moles of substance you're having in a unit volume, in other words, an increase in concentration, that will make the reaction take place faster. In other words, great, large concentrations. Okay, allow me to just write conc for concentration. This, if you have got high concentrations, those substances in high concentrations will react faster or will cause the reaction to take place faster. If you lower the concentration by having less moles per unit volume, the reaction will take place slower. Okay, you can maybe think of a real life situation where you're doing your washing. If you keep your water in that particular bath or bowl or wherever you're doing your washing in, if you keep the water constant, you don't change the amount of water that is there, but you change the amount of washing soap that you are using. If you put 1 scoop into the same amount of water and you wash, maybe the washing may not take place that faster. The reaction between the soap and the dirt on your cloth may not be taking place that faster. But if you put 2 scoops of soap, washing powder, in the same amount of water, and you put your clothes in, this time the reaction will take place faster. You will also feel it yourself as you do your washing. If you're doing it manually, not using your machine, you will feel it that actually now it's happening faster than before. Why? Because with 2 scoops of washing powder, you have increased the number of moles of soap inside that solution. Okay? You have kept the level of water the same, or the volume of water the same, but all you did was to increase the concentration. So if you increase concentration of something, you are going to cause the reaction to take place faster. So in the same way, if you decrease the concentration, you're going, or if you use something of lower concentration, you're going to make the reaction take place slower. Okay. Now, state of division. Okay, I said here it is something to do with surface area and even the size together. Okay, these two can actually be worked on to make the reaction take place faster as well. For example, if you have got pieces of chalk, for example, the chalk that you use to write on a board, and you want to dissolve it in water, if you just throw those pieces of chalk in water, it might take a longer time for the pieces of chalk to dissolve. But if you decide to grind the chalk into powder, that will make your dissolving of chalk in water even faster. Okay, but sometimes you may also say, look, I'm not going to grind it into powder. All I'm going to do is to cut it into smaller pieces. So instead of a chalk of that size thrown into water, I'm going to cut it into smaller pieces of, say, 10 centimeters, 10 centimeters, 10 centimeters. And you throw it in there. Obviously, it will react faster compared to when you have got the whole chalk unbroken thrown into that water. Okay, so that is what we're talking about with the question of the state of division of the solids when you are having a chemical reaction. And you can see that the more fine the substance is, the more you have grounded it into fine powder, the faster the reaction. Okay? And when we say that when you have done that, you have actually increased the surface area and you have decreased the size of your reacting substance. So when you increase the surface area, you are increasing the rate of reaction. So let me put that in here. Increase in surface area, you are causing the reaction to be faster. Faster reaction. Okay, so that's what you need to know. With a catalyst, we have discussed it already. We know this is a substance that is used to speed up the rate of reaction without taking part in that reaction. Perhaps to give a real-life situation here or real-life example, you can think of the bicarbonate of soda, something that is called cooking soda. If you want your veggies to cook quicker, normally you would use bits of the bicarbonate of soda in it so that it cooks quicker. The bicarbonate of soda, what it does is just to soften it and make it to react faster. So you can look at that as something that can represent or that we can understand to be a catalyst, something that makes a chemical reaction to take place faster without taking part in that reaction. All right, now let's move on to example 2. Which one of the following would not change the rate of a chemical reaction? Now, this is a multiple choice question. This is a multiple choice question. Okay? We have got 4 possible answers to it. The statement is saying which one will not change the rate of reaction. Let's look at the possible answers. A change in the amount of reactants. Wow, amount of reactants. Amount, something we didn't say much since we started this lesson, huh? But then let's see if we go through the whole lot, the rest, number B, C, and D, and see whether we can find something that will not speed up the rate of reaction or will not change the rate of reaction. Let's come to B. B says, a change in the temperature. Oh, yeah, this one we're familiar with. We know temperature definitely changes the rate of reaction. A change in the surface area. Oh, definitely. This one changes the rate of reaction. And the last one, D, a change in the concentration. Oh, we have spoken about this one. Change in the concentration of the reactants. Okay, so B, C, and D, we have found all these ones to be factors that will affect the rate of reaction. In other words, changing these ones will change the rate of reaction. But then let's go back to A. Definitely this should be the answer. This should be the answer that will not change the rate of reaction. Okay? Now, amount. Maybe we need to talk about that word there scientifically. Amount just refers to how much of something you're having. Okay? It doesn't tell us about a real factor that will affect the rate of reaction. In other words, if I go back to the example of chalk, dissolving chalk in water, if I have one piece of chalk, it can still help me to tell how fast it will take to dissolve in that water. So whether I increase it to 2 pieces of chalk, 3 pieces of chalk, 4 pieces of chalk, I will still be having chalk. That is the thing. So all I did was to increase the amount of chalk in there. All right. So it's not going to affect how fast or how slow that chemical reaction is going to take place. All right. Now let's move on. Let's come to example 3. Example 3. Now you listen carefully here. 5 grams of zinc granules, mark that word, are added to 400 cubic centimeters of a 0.5 mole per cubic decimeter hydrochloric acid. Okay? So this is your concentration, number of moles per unit volume, mole per cubic decimeter. To investigate the rate of the reaction, the change in the mass of an open flask, containing the zinc granules and the acid, in other words, your reacting mixture, was measured. This was done by placing a mass balance under that container. So you have something like that. You have a container here with zinc and acid here. So HCl and zinc in there, Zn, zinc. Okay? So you put a mass meter down here. Something that will tell us it has got digits there. It will be reading, okay? Of course, connected to a power supply somewhere there. It will give us how fast the mass is changing as the reaction takes place there. And it's an open flask, so it's not closed up here. It's not closed, it's open. The readings collected show that there is a decrease in mass during the reaction. The reaction which takes place is given by the following equation. So we have Zn, zinc in solid form, reacting with HCl in solution, aqueous, and giving us zinc chloride in that solution, and the gas hydrogen formed as well. Now remember that the container here is open. What does it mean? So this gas is actually escaping into the atmosphere because it's just a gas. All right. Now, first question, why is there a decrease in mass during the reaction? Why are we seeing a decrease in mass? This meter here shows us a decrease in mass. Well, the answer is exactly what I have explained in terms of hydrogen. Remember, one of the products is hydrogen, okay? So the H2 gas, it's escaping into the atmosphere because the container is open. So the H2 gas formed escapes into the atmosphere. Why? Because since the what? The flask is open. So the flask is open, the gas is escaping into the atmosphere. So the mass should be decreasing. Right, coming to number B, the experiment is repeated this time, and we are using 5 grams of powdered zinc instead of granulated zinc. How will this change the rate of reaction? Explain your answer. How will it change? And then explain your answer. Okay, now you're using the same amount of zinc you started with, it's 5 grams. The only thing you did was to move from, so you had 5 grams granules, zinc granules. Okay, that is the initial stage. Now you are having 5 grams, but what have you done now? You now have 5 grams of zinc powder. Okay, now 5 grams of zinc powder. Will this change the rate of reaction? Exactly yes. The answer is yes. The rate of change of reaction is going to change. How will it change? The reaction rate will be faster compared. The reaction rate will be faster. Okay, this time it will be faster compared to A when zinc granules were used. Zinc granules were used. Okay, so that's what we can say. What backs us up in this conclusion is that with a higher surface area, the reaction rate increases. Okay? Reaction rate increases. The reaction rate increases. Okay. Now, this is the understanding we should be having. You don't have to be rewriting it, but I'm writing it down because this is where it comes from for us to conclude that when we are using the zinc powder here, the reaction rate will be faster than when you're using zinc granules. Okay, right. So when you use zinc granules, the reaction rate will be affected and it will be faster actually. And then in explaining our answer, we need to talk about the fact that we're using powder this time and there's an increase in the surface area. Let's come to number C. The experiment is repeated once more. Okay, this time using 5 grams of granulated zinc, so it's like right at the beginning. But then we're using 600 cubic centimeters of 0.5 mole per cubic decimeter hydrochloric acid. How does the rate of reaction compare to the original one? Now, what has been changed here if we go back to the original situation? Let's just look at that quickly. At the beginning, what we had, it's 5 grams granulated zinc. The concentration is 0.5. It hasn't changed. So these two items here have not changed for case number 3 that we're looking at. But then what has changed is at the beginning we had 400 cubic centimeters. Now we're looking at 600 cubic centimeters. In other words, we have increased the volume, the amount, if you like, of hydrochloric acid. How will the reaction rate compare to the initial one? Okay? Now, the reaction rate is going to be the same as at the beginning. Why? Okay, so reaction rate will be the same, as at the beginning. Why? Why? Because you're having two things there. One, factors that affect the rate of reaction, its surface area, which has got something to do with the zinc granules. So we still have zinc granules. Okay? Two, another factor there that will affect the rate of reaction there is actually the concentration. We started with 0.5 concentration. We started with 0.5 mole per cubic decimeter. We're still working with 0.5 mole per cubic decimeter. The only thing that has been changed, let me put a dot to it, is the amount of acid. Amount of acid, we started with 400. We are now using 600 cubic centimeters. So all we have changed is the amount of the acid. Now remember what I said about the amount earlier on. If you change the amount of a substance, you are not going to change the rate of reaction, because this is not a factor that will affect the rate of reaction. Hence, we are saying that the reaction rate will be the same as at the beginning, at the start of this chemical reaction. Now, before moving on, I want to talk about something here, because you can see that here we're looking at something that has to do with practical investigations. And there is a lot of opportunities here under rates of reactions for you to do practical investigations. Okay, practical investigation, you would see that when you are investigating one factor, every other factor must remain constant. Okay, so if I am investigating the effect of concentration, allow me to just write conc. If I'm investigating the effect of concentration on chemical reaction, it means that temperature, state of division or surface area, state of division, okay, I've spoken concentration, so temperature, state of division. I shouldn't be, if I didn't use a catalyst, so I mustn't be taking any catalyst in because it will affect my results. I shouldn't be changing the states in which, or the nature of reacting substances, okay? Reacting substances. Now, all I'm trying to say here is that when you are doing a practical investigation, you will be looking at change in concentration and how long, so time. These are the only quantities that you're going to look at in terms of checking their relationship. So keep everything else constant. We say scientifically that every other variable here is controlled. Okay? So this is the control, these are the controlled variables. You can list them. Right. Remember that when we're looking at gases, okay? When we're looking at gases, we will be looking at pressure as one factor that affects the rate of reaction. But why didn't we single it out here? Because when we look at gases and look at pressure, pressure is equivalent to, it's actually about concentration of that gas. So that's why we are not really talking about it in that way, because concentration sort of caters for that particular situation where we're looking at a gas. Obviously, in the same way, the higher the pressure, the faster will be the rate of reaction. Right, let's proceed. And now we're going to talk about how can we represent the process of chemical change, chemical reaction, graphically, the rate to be specific. We're going to look at that on how, and specifically on how we can graph this, put it in a nice short graph, and we can tell how the reaction is taking place in terms of its speed. Okay, now, so it's reaction rate and graphs. Here, the graphs that we're going to look at, or that we can use, we can look at a graph that talks about the mass changing over time. So here what we are saying is that you can graph, for example, we know that time will always be on our horizontal axis in a graph, so time in seconds. And then this vertical axis will then be representing the mass, and this will be in grams. Okay, so that is the graph that we'll be looking at if we were to graph the change in mass over change in, in a period of time. The second part is that we can also look at temperature changes. Okay, how is temperature changing? And of course, per unit time. In the same way, this on the vertical axis, you'll be having the temperature in degrees Celsius or in Kelvin, and then you would have on your horizontal axis the change in time. Okay, and then we will also look at graphs representing energy changes. Okay, now energy changes, again, course of reaction or the time it takes for the reaction to take place, and we're looking now at what change in energy is happening from reactants to products. And then in that way, it means up here we'll be having energy in joules or kilojoules, or joules per mole or kilojoules per mole, and then here we'll be having the time or the course of reaction. So these are the graphs that we can use to represent what is happening in that process of chemical reaction. Either we can be looking at the graph that would tell us the change in mass over a period of time, or we can look at what happens with the temperature over a period of time, and we can also look at energy changes. Now with energy changes, we're going to look at where is the level of our reactants in terms of energy state before reacting, and then check what happens with the products. Where are the products? Are they at the same energy states, or has there been any changes in energy states? Now the energies, of course, measured in kilojoules or joules, or kilojoules per mole or joules per mole. Right, let's move on and have a look at some of these graphs. Now here we're looking at reaction rate put in a graph form. Like I said, you will have your time measured in seconds on your horizontal axis, and you will have mass measured in grams on your vertical axis. All right, now, if you are collecting the gas, for example, let me write down what was happening with the zinc. So you had zinc, solid, reacting with hydrochloric acid, remember? And these gave us zinc chloride. Okay, this was in solution, plus hydrogen, which was in a form of gas. This one is AQ, the hydrochloric acid, sorry about that. So what we are seeing here is that hydrogen is given off as a gas in this reaction. Now, if we had that open container with a mass meter here, the mass will be decreasing, okay? But if we are looking at this reaction such that we have something that is going to help us to collect the gas. So say we put a tube here, and collect the gas into some container here. And this time put our mass meter down there. Now as the gas fills up this container, the mass of this container is going to increase. The mass we see on this mass meter here is going to increase, whilst the mass there will be decreasing. Now, the mass showing us the accumulated gas will be increasing, and you would see here when you are collecting a gas, all right, there is an increase. That means an increase there, okay? There is an increase in the amount of mass that you are having. But there is a time when that increase sort of stops, okay? It stops there if we look at our graph. Now, what has happened when it has stopped there? It means at this time, at this point in time, let me call it T1, time 1. At that point, the reaction has taken place from there, okay, and we are collecting the gas. The mass of the gas is increasing, and it reaches a point, okay? It reaches a point where it is some value, okay? Started from 0, there was nothing in that container first. It builds up to some value there, and that is that point there, and it levels up. What is happening between T1 and, let me put T2 there? What is happening there? Between T1 and T2, we are seeing a leveling up. In other words, the mass is not changing anymore. What has happened? It means our reaction at this point has stopped. Okay, the reaction has stopped at that point there. Okay, between T1 and T2, the reaction has stopped. It's not happening anymore. But between 0 time and T1, what is happening? The reaction is taking place, and the mass of the gas is increasing. So reaction takes place here. Reaction is occurring there, okay? And then what is happening? What is happening there? What is happening is that mass of gas is increasing here. Mass of gas is increasing. So at that point, at this portion here of our graph, we are seeing the mass of the gas increasing. Here, when the reaction has stopped, what is happening? Mass of gas stays the same. And that tells us that the reaction has stopped. Okay, so that's what is happening there. Now let's look at the sort of reverse of what we started with here. Let's say we're looking at a situation where the mass is lost. Okay, there is loss of mass. So suppose we're looking at the same situation, and you have got your open container this time, not closed. And you have got your mass meter placed underneath. So it's giving us readings as the reaction takes place. Inside here, we have got the reacting substances in here. They are reacting. Okay? So, and as that reaction takes place, this is an open container. The gas comes out, bubbles out. The H2 as it is formed, if we're looking at that example of zinc and hydrochloric acid reacting, the H2 escapes into the atmosphere. What do we expect to see happening in our scale here? It should be telling us loss of mass. In other words, you start from a higher mass, and the mass is gradually getting smaller and smaller over there. Okay? And How can we graph that? Look at it. You start with the actual mass that was given to you. So it's some mass, you can see it's not zero. It's some mass that it's up there at some point. But with time, as the reaction takes place, the mass gradually decreases. Okay? Okay? If you look at this graph here, I want you to notice something as well, which even with the earlier one, it is there, but we didn't really look at it. From there to there, we have got a nice sharp decline of the mass. Okay? Nice sharp decline of the mass. And here we have got some curve here up to that point. Okay? Let me call this one T1. Let me call this one T2. And let me call that T3. Okay? Now, from 0 to T1, which is this area here, we've got a sharp decline in the mass. But between T1 and T2, we've got some curve, the gentle curve. And that tells us that the reaction rate is slowing down at that point. Rate slowing down. So we've got the reaction rate slowing down there. And like in the previous one, between T2 and T3, we have got a reaction that has stopped happening. So reaction stopped there. Okay? Reaction stopped. Okay? And now, here, what can we say about it? Reaction rate is quite fast there. The rate is fast there. We're losing more of the mass than between T1 and T2. Okay, so that's what is happening. Right, so those are some of the graphs that we can use to represent reaction rates. Okay, now let's move on and look at another example. This will be example 4. Example 4 is a question based on investigation, of course. It says, a group of learners wish to investigate the effect of concentration. So it's concentration that they want to know about. They want to know what effect does it have on the reaction of calcium carbonate and hydrochloric acid. Okay? Now they collect the following apparatus for their investigation. They've got large calcium carbonate chips, they've got small calcium carbonate chips, they've got powdered calcium carbonate. They also have 2 mole per cubic decimeter. If you see this capital letter M here all the time, it represents mole per cubic decimeter. They've got 2 mole per cubic decimeter hydrochloric acid. They've got 1 mole per cubic decimeter hydrochloric acid. They've got 0.1 mole per cubic decimeter hydrochloric acid. Okay? And then they also have a scale. Right? They have a stopwatch. They also have measuring cylinder. 2-holed stoppered flask. Okay? I think here maybe it could be for collection of gas. Large beaker. They've got a burette, a thermometer, spirit burner, and gas syringe. Okay. Now, question is, what apparatus should they select to investigate the effect of concentration? What apparatus should they select? If we go back to what has been given to us, if you are investigating concentration, it means you should be changing it. And for you to change it, it means you must have these 3 solutions here. You must have solution with a high concentration, somewhere in the middle of a concentration, and very, very low concentration of hydrochloric acid. So they would have that, okay? What else are they going to have? They would have to choose just one of this. They cannot choose more than one. If they want to go for large calcium carbonate chips, they should go for that and keep it constant, because what they want to check is concentration. And obviously, because they are going to have calcium carbonate reacting with hydrochloric acid, there would be gases formed. You want to make sure that the mass is kept constant as well. Right, now let's find the answers to that question, or to this question. We have seen that obviously you are investigating the concentration, so you would have the 3 samples. So let me use number 3 samples of HCl. Okay, you will have that. But you need to take 1 sample of calcium carbonate. So if you want to go for the lumps, you go for them. If you want to go for the powder, you go for the powder. But you keep it constant for all your investigation, because that must be your controlled variable. What else should you ensure? Another thing that you should ensure is that you need to have fixed amount of acid. So although you're taking the 3 samples of acid in terms of the varied concentration, but the volume, okay, should be fixed. So fixed volume of acid to ensure that not any other factor is going to affect your results except what you are investigating. Okay? And then another thing that you would need to look at is you would have to have your thermometer. And what will be the thermometer doing here? You want to keep the temperature the same. So you want to be measuring it all the time. Okay? So you will need that apparatus as well. And then you would also need your flask. You will need your flask. You will need your scale, because you want to measure the changes. And you also need your stopwatch. This is very important. We're measuring the rate, so time is very important. So you would need your stopwatch there. Right, here you would also need a burette. Okay, you would also need the gas syringe. And you'll need, as well as the last one here, you need your measuring cylinder, because you want to know or measure exact amounts of the acid. So you need the measuring cylinder as well. Okay, so these are all the apparatus that you would need to put together for this practical investigation. Now let's move on to number B. Number B says, list the steps they should follow for this investigation. And let's have some space for that quickly. I'll try and summarize it. 1, we know that they need to weigh, okay? They need to weigh the calcium carbonate chips, okay? So they weigh them. They need to make sure that if it's 5 grams, all of them are 5 grams in the 3 samples of the acid, okay? So you put this into 3 different flasks. So place the chips in 3 different flasks. And here, when you have done that, you would need then to connect the burette and gas syringe. Oh, that's that spelling. you need to connect the burette and the gas syringe into each flask. You also need to place the thermometer in the water. And let me just say hot water here. And this hot water should be the water in which the flask is in. So all these 3 flasks should be inside this water. So you place the thermometer in the water, in the hot water beakers or whatever you might have used, because where the flasks are. Okay, now this is for you to measure the temperature as the reaction takes place. Now when you've done that, then you add the 3 samples of acid, okay, in the flasks respectively. And start the stopwatch. Okay. Right, so when you start the stopwatch, you're going to measure the time or take records of the time every 30 seconds for 5 minutes. Measure the time or record the time for 5 seconds or for 5 minutes, okay? And in that way, you're going to be able to see how fast is the reaction taking place in the 3 flasks where only the concentration is the factor or is actually the variable that is changing. All right, so remember, this is a way of trying to help you how to put together a method, but then you sit down and you structure it yourself. You can come up with something very similar to this, not exactly the same. But the issue here is that you need to be able to know how to put in your methods, how to put in your practical investigation in such a way that somebody else can actually follow your method and perform the same practical. Right, let's now move on to the next question, which is number C. After collecting one set of data for this experiment, one of the learners suggests that they should rather use powdered calcium carbonate rather than the chips that they are using there. Is this a good idea? Okay, explain your answer. Definitely this is not a good idea. Why is it not a good idea? Not a good idea because what is under investigation here is concentration. Every other variable must be kept constant. Okay, so if you use powder, you are actually now looking at surface area. Let me use SA for surface area. So you now have surface area and concentration, and then looking at how they both affect rate of reaction together, that's not going to be a fair test. So this is not a good idea because it will not be a fair test. It will not be a fair test. Okay, we need to have a fair test. What is a fair test? Only one variable should be changing. In this case, it should be concentration. Only concentration must be changed. Okay, only concentration must be changed. All other variables must be constant, must be kept constant. We say they must be controlled, they must be kept constant. So it's not a good idea to change the state of division for the chips into powder. All right. D, draw sketch graphs comparing the rate of reaction when 50 cubic centimeters, 50 cubic centimeters. So volume is kept the same, but then the concentration have been changed. 1 mole per cubic decimeter HCl, 2 mole mole per cubic decimeter HCl. The temperature is also kept constant. The only thing that is changing, you can see there, is the concentration. Now, we know here the reaction will be, the rate will be lower compared to the rate here because this part here is more concentrated. Right, so if I were to draw the axis here, so I have my horizontal axis there, that's my vertical axis. And of course, this will be my volume axis measured in cubic centimeters. This will be my time axis measured in seconds. You would see that if I have a 2 mole per cubic decimeter, I expect the reaction rate to be faster, so the volume of the gas should be formed quite quicker like that, and then I'll have the gentle curve and I'll have it leveling up there. Okay, but when I have 0.1 moles, the reaction rate will take place in that way, slowly and curving up there, and of course they are going to meet there. Okay, and then what does this mean? It means that when I have a 2.0 mole per cubic decimeter, and when I have got a 0.1 mole per cubic decimeter, the reaction rate won't be the same. It will be slower here, and it will be faster there. Okay, so that's what I'm going to have. Right, let's look at the next combination here. Okay, in the next combination, what we have is, perhaps let's go back to that slide so that we see exactly what is happening here. You have here, we have here this combination now. We have got we've got 100 cubic centimeters, 50 cubic centimeters. So what has changed here is the amount of the acid. You've got the same concentration, the same temperature. What is going to happen here? Okay, and there's something that perhaps we're going to assume here, because we know that the rate of reaction is not going to really change because of changing the amounts here. But then perhaps as to where it is going to stop, it will depend on the amount of acid that we're having as well. So allow me to quickly draw another set of axes here. So there is another set of axes. Then here you've got your time in seconds, okay? You've got your volume in cubic centimeters again. So what is going to happen now? You're going to have a situation where the reaction rate would be the same. It may stop there if the mass of the marble chips is finished, or if you have got enough of the marble chips, okay, to take it up to that point in terms of what has been the yield. You can have something like that. But what I want to emphasize is that you will see that this part of your graphs, both of them, where you have got 500 cubic centimeters and where you've got, the 51, this is less. All it is saying here is that here you have got the same rate. The only thing is that in one instance it will continue to react as long as you have enough marbles. But if here your marbles are finished, it's going to stop there. The rates are going to be the same because the amount of the acid does not play a role in changing the rate of chemical reaction. So basically that is how the graphs can come about. We have to end it here, but then you need to have a look at the notes and check. There will be more graphs there that I will be talking about energy changes and temperature changes in a chemical reaction. Thank you so much for watching. Hope the lesson was helpful to you. Keep well. Bye-bye.